Hello everyone, welcome to the live session of Basic Linear Algebra week 6. So before starting the session, let's clear off some doubts which we had in the last session. So there was a doubt in there was a discussion going on this question. So okay, so let's see that first. Okay. Okay, so the question was if T is linear transformation such that T of x comma y is equal to 2x plus y comma x minus y, then find transformation from basis b1 to b2 if a is if b1 is and b2 is yeah. So first we'll substitute 0.11 from basis 1 here, and we'll find it and we'll find the transformation. Which will give me 3 comma 0 and so this is going to give 1 comma 2. So now we have to express these as a linear combination of basis 2. Okay, so now linear combination of basis 2. So there was a mistake done by me in this place, so I am telling the corrected version now, correct solution now. So now if you solve this, 2a minus b is equal to 3 and a plus b is equal to 0. So with this you'll be getting a is equal to minus b, and we'll be getting 3a is equal to 3, which is a is equal to 1 and b is equal to minus 1. So 1 comma minus, so this is our first column. Similarly for the other point, we again express as a linear combination, which will give us 2a minus b, a plus b, so 1 comma 2. So 2a minus b should be equals to 1 and a plus b should be equals to 2, and which means that a will be equals to 1 and b is equal to 1. So 1 comma 1, this is our second column. So this would be our so this is our so there was a mistake done the last time, and so I think Manideepa ma'am, you told me this solution. So so it's I think it will be +1. So that is so this, thank you for pointing it out that the mistake. So if in case for the same question, if base 2 is the standard basis, then we can directly express it as a form of 3 of 1 comma 0 plus 0 of 0 comma 0 and 0 comma 1, and then we'll be getting first column as 3 comma 0, and the second column will be getting as 1 of 1 comma 0 plus 2 of 0 comma 1, like that. So this will be our second column if in case the basis which we have is standard basis. So I hope this clears the things, everything. Okay, so moving on to the questions for the topics discussed on the week 6 in the recording session by the professor. So in the first lecture, the topics discussed were about the isometries. So let's try to answer some true or false questions. So if it is true, why it is, if the statement is true, why it is true, and if it is false, then what would be the correct statement. Okay, so the statement is, if P is an isometry, then its matrix representation must be orthogonal matrix. So this is true or false? Yeah? What do you think? It is true or false?
Ma'am, I think it is true.
Yeah, so why do you think it is true? Okay.
I think orthogonal matrix may preserve angle.
Okay, so first of all, okay, so the properties of isometric matrix is first of all the lengths of the vectors are preserved, length is preserved, and also the length is preserved, and also the angles between the vectors will be preserved. So these two conditions should be there. Okay, so let's see first of all this condition. So suppose you have a suppose this is matrix representation is V for the isometric transformation, then the norm should be equals to this. So this is the first statement. So now, as I told that it's represented by matrix A, this must be true. Okay, and norm of the vectors is given by, yeah, so this we already know. So how can we write this is this equals to V transpose. So the same thing here, and left hand side, right hand side. So we are trying to prove this. Okay, so how can I write this? Square root of V transpose, A transpose, and then A and V is equal to V transpose V. So I'm just squaring on both sides. Then V transpose A transpose into A into V is equal to V transpose V. So V transpose so which means that if this both has to be equal, then A transpose A should be equals to identity matrix. Okay, so this has to be orthogonal. So this will be orthogonal if so for preserving the length constant length after the transformation. Okay, and then if we see regarding if the angles are preserved, it means that suppose if I'm taking two vectors u and v, so dot product should be same for the angles between the vectors to be same. Okay, so this we can write as vector representation. So we know this. So U transpose A transpose into A V is equal to U transpose V. So similarly again, so this has to be orthogonal identity matrix so that this equation satisfies. So A transpose A is equal to identity matrix, which means that A is orthogonal matrix. So for this, the statement is true. I hope this is clear. Okay, so moving on to next question. So every orthogonal matrix is an isometry. True or false? What do you think? Every orthogonal matrix is an isometry.
I think true, ma'am.
Yeah, that is true. True statement. As we have seen in the previous exercise. So for all the orthogonal matrix, the norms like the norm and the angle both will be preserved. So orthogonal matrix is isometry. Okay. So next question. Determinant of isometric transformation matrix is always 1. True or false? So of isometric transformation matrix, determinant is always 1. So true or false? If it is true, why it is true? If it is false, then what will be the what will be the correct statement?
I think it is false.
Yeah. So what is the right statement?
I think determinant of A should be plus minus 1. Determinant of the isometric
Yeah,
transformation.
true. So
Because
determinant will be plus or minus 1. We'll see how it is. So A transpose A is as we saw that every isometric transformation matrix will be orthogonal matrix, so this will be satisfied. So if we see the determinant for this, so that would be 1. It should be 1. So determinant of A transpose A can be written as determinant of A transpose determinant of A. why is it so? Like if you have seen the week 4 session which I have discussed, even a question I have given saying that the statement 1 as AB is equal to BA, and statement 2 as determinant of AB is equal to determinant of BA is equal to determinant of AB is equal to determinant of A into determinant of B, right? Like there was a question discussed whether this is true or false. So though the matrix multiplication may not be commutative, but determinant AB can be written as determinant of A comma B. We saw it by splitting it into elementary matrices. So this can be written as determinant of A into determinant of B. So we know that determinant of A transpose will be same as determinant of A. So which means we can write like this. So determinant of A will be plus or minus 1. It's not just 1. So it's plus or minus 1. So for that it's false. Okay. So another true or false question. So if a linear transformation T is an isometry, then both column vectors and row vectors of its matrix representation from orthogonal sets. So it's true or false?
True, ma'am.
Yeah. So why?
Because isometry preserves length and angle.
So what will happen? So as we saw that so if the matrix representation is orthogonal, so it means that, like, for example, if we just take you can write it like even both will be anti-matrix, right? So suppose if I'm taking A as A B C D, and then A transpose will be equals to A B C D, right? So then A transpose A so this will be multiplied with this thing, right? And that will be equals to 1. So this vector these vectors, column vectors, so for A, suppose the row vector, okay, so AC here in A is column vector. So AC, if you see that column vectors, if you multiply, you are going to get 1, which means that these vectors are orthogonal. Similarly, if you see this thing, again you will be getting because this is orthogonal I said, so this is going to be 1 0 0 1. So the product, so this is going to be 1 0 0 1, right? So this into this will be 1, and this into this element also is going to be 1. Okay, so the column vectors, they are going to be so we saw here that column vectors are going to be orthogonal because the product of the vectors is dot product of the vectors is going to be 1. And also if you so if you take that example of A transpose A, you can prove that column vectors are orthogonal. And if you see similarly for A transpose, then you can find that row vectors will be orthogonal. So it's going to be 1 0 0 1. So this this is row, first row, and this thing. So if you multiply this, you'll be getting this element, and if you multiply this, you'll be this element. Okay, so these are going to be orthogonal. So so if a linear transformation T is isometry, then for the matrix representation, whatever the column vectors and row vectors you have in the matrix representation, those will be forming the orthogonal sets. That's true statement. Okay, so moving on to next question. So statement is inverse of orthogonal matrix is not orthogonal.
For the last question, even we can say it is orthonormal set, right?
Yeah, so if
Orthonormal
it is
sets.
normalized orthogonal, if it is
Because-
normalized, that will be orthogonal.
Yeah, because I think the lengths also we are getting as 1.
Yeah,
So
yeah.
orthonormal sets also will be okay.
I can say that.
Yeah, okay.
Yeah. So inverse of so next question, the statement is inverse of orthogonal matrix is not orthogonal. So that is a true statement or false statement. If it is true, why it is true. If it is false, why it is false, and what is the right statement? Yeah. So what do you say for this? So inverse of orthogonal matrix, will it be orthogonal or not? Yeah. So basically, what is
It will be
orthogonal?
orthogonal.
Yeah. Should we wait?
It will be orthogonal.
Yeah. It's a false statement.
Yeah, it's a false statement.
Yeah. So what do you? So what is it? How do we get this? So A into A transformation. A into E transpose is.
A into A transpose equals to identity. So A transpose is the inverse of A.
Yeah. So A transpose is going to be inverse. So I want to check with whether this will be I or not. Okay. So as I said here, so A inverse is A transpose. So I can write it like this. And so A transpose of transpose is going to be I, so which means that A transpose A is equal to I. So yeah, so that satisfies, right? So so this is going to be orthogonal. So even the inverse is going to be orthogonal. So this is a false statement. Okay, another question. Product of two orthogonal matrices need not be orthogonal always. This is true or false? So if two matrices are orthogonal, will the product be orthogonal or not? Okay, shall I tell the answer?
It is false statement.
Yeah, but
It has to be orthogonal.
okay, so it's a false statement. So we check how it is. So suppose A and B both are orthogonal. Given that A and B both are orthogonal, then we have to check whether this is orthogonal or not. So for AB to be orthogonal, so suppose AB is equal to C, then if C transpose C is equal to I, then it is orthogonal, right? So if AB transpose into AB, what will be? So it will be B transpose A transpose into A into B, right? So I said A and B both are orthogonal, means A transpose A is going to be orthogonal, so this is going to satisfy, and even B transpose B is equal to be I, so even this will satisfy, right? So B transpose A into B, so that's going to be B transpose I into B, and this again is going to be I, so which means that AB transpose and AB product, it's going to be orthogonal. So the product of two matrices, if they are if the product of two orthogonal matrices, they are going to be orthogonal always. So that's it's mentioned it's not, so it's going to be a false statement. Okay, so for a given matrix, so this is going to be a bit lengthier, but please do it so that we get a hands-on experience. So this is a matrix given. So I want you to find eigenvalues and eigenvectors corresponding eigenvectors, and then find what is the multiplicity of each eigenvalue, and what is the defect of each eigenvalue, and tell me whether it is whether it can be diagonalized or not. Diagonalization is possible or not? So for the given matrix, answer all these questions. Okay, so let's do it together. So first of all, how do we find eigenvalues? So if a matrix A is given, so that means A minus lambda I, the determinant of it should be 0. For that we'll be solving it and we'll find the lambda values. Minus 1 minus lambda 0, 12, 0, 0, 1 minus lambda 0, 12, 0, 0, minus 1 minus lambda minus 4, 0, 0, minus 4 minus 1 minus lambda. Okay, so determinant of this has to be 0. So if you open it, so it's a 4x4 matrix, but so many zeros entries are there, so calculation should not be that difficult. So determinant, so we have all three zeros here, so we can just multiply this with this submatrix, determinant of this matrix, then we'll be getting it. Even here also, if all the zeros are here, so plus lambda, 1 minus lambda, and this can be written as lambda plus 1 minus 4 lambda plus 1 plus 4, right? So we can factorize, ultimately we can factorize it like this. So eigenvalues did you get as 1 minus 1, 3 and minus 5? So did you reach till here? So it's a 4 by 4 matrix, but it's a simple one because you have all zeros here. So if minus 1 minus lambda into, even this if you're multiplying, then 1 minus lambda into, if you're just doing this minus 1 minus lambda into minus 1 minus lambda minus of 16, so you can really get like this. And so this is anyways outside, and 1 minus lambda is also in factor form only, and so here it is like you can write it as minus of 1 plus lambda the whole square minus 16, which is 4 square. So it's in the form of a square minus b square. So a square minus b square is a minus b and a plus b. So that was written in this form, a minus b and a plus b. So ultimately you can get it in as a the factors here as mentioned here. So you can get it as lambda as so it is, you have to equate this as 0, and this is equal to 0. So minus goes there, and then lambda is 1 minus 1 3 and minus 4. Okay, I hope you got till here. Okay, so what is the multiplicity here?
1.
Yeah, so multiplicity, because everything is unique, right? So only one is there, only this one time it's there. So here it's it's not repeating, nothing is repeating. Okay, so 1 is coming only once, minus 1 is coming only once, 3 is coming once, and minus 5 is coming once. So for all the eigenvalues, the multiplicity is going to be 1. Okay, so this is answer. And then now let's find eigenvectors for this. For minus 1 eigenvalue, let's find eigenvector. So eigenvector, how will you find? Lambda I x is equal to, so you'll solve this, and you'll place each lambda value here, and correspondingly you'll get eigenvector there. So 1 minus 1 minus lambda 0, 0. Let's do it for minus 1. So lambda is minus 1, so we are going to get as so if you solve this, so you can get as x3 is equal to 0 minus 4 x4 is equal to 0. If you expand this, 2 into x2 plus 12 into x3 is equal to 0, and 12 into
x4 0.
x3 is equal to 0. Okay, so here from this x3 is equal to 0 is clear, x4 is equal to 0, and it's like x2 is equal to minus 6x3 and x3 is equal to 0, so even x2 is going to be 0, and there is nothing given on x1, right? So x1 will take it as arbitrary. So
Excuse me, ma'am.
yeah,
Third equation should be 2x2 plus 12x4.
2
Third
x2
equation.
plus 12 x4. Okay, fine. Yeah, anyways, they are also 0, right? So even x4 is 0. So so both x1 so x2 x3 x4 are going to be 0, and so we can get eigenvalue for the corresponding to lambda value minus 1 as this. Okay, let's solve for eigenvalue 1. So again, minus 1 is same thing. We minus it. So you have to solve this for getting eigenvalue plus eigenvector corresponding to eigenvalue 1. So if you put 1, then you are going to get minus 2, 0, 12, 0, 0, 1 is going to be 0, 0, 12, and 0, 0 is going to be minus 2, minus 4, 0, 0, minus 4, and minus 2. So yeah, if we know all these things already, let's okay. So it's going to be minus 4x3 minus 2x4 going to be 0, minus 2x3 minus 4x4 going to be 0 again, and then 12x3 sorry x4 is going to be 0, and minus 2x1 plus 12x3 is going to be 0, right? So from here x4 is going to be 0, that's clear for us, and from these two equations we can get x3 is also 0, and if x3 is 0, then from this equation we'll get as x1 as 0. So x2 is not x2 will be the arbitrary we couldn't find here. So 0 t 0 0 some arbitrary constant. So you can pull it out. Okay, so this is eigenvector for lambda is equal to 1. Okay, so fine, let's do it. So lambda is equal to 3. It's going to be minus 4, 0, 12, 0, 0, minus 2, 0, 12, 0, 0, minus 4, 4, sorry, minus 4, 0, 0, minus 4, minus 4. Okay, so minus x3 minus 4x3 minus 4x4 is going to be 0 here, and minus 4x again the same thing, minus 4x4 is again going to be 0 here, and then 2 into x2 plus 12 into x4 again 0 here, and minus 4x1 plus 12x3 will be 0. So x3 is going to be equals to minus x4, right? And x2 will be equal to 6x4, and x1 will be equal to 3x3, which is equals to 3 of minus x4. Okay, so suppose if I am taking x4 as an arbitrary constant t, then I can write it as 1, and x1 will be minus 3, 6, and x3 will be minus 1. Yeah, minus 1. So this would be your eigenvector for lambda is equal to 3. So similarly lambda is equal to 4.
Another one eigenvalue is -5, right? Or is it 4?
Sorry?
Just -5, I guess.
-5.
Sure, yeah,
Hmm.
-5. Okay, if we solve the equations, x3 minus 4x3 minus 4x4 is equal to 0, and 6x2 plus 12x4 is equal to 0, and 4x1 plus 12x3 is equal to 0. So x3 will be equal to x4, and x2 will be equal to minus 2x4, and x1 will be equal to minus 3x3. So okay, so x4, let's take it as arbitrary value. Then x1 will be minus 3, x2 will be minus 2, x3 will be 1. Okay, so like let's write every okay, so we have eigenvalues as okay, so I get -1, 1, 3, and -5, and corresponding eigenvectors we had so yeah, so did you get this?
Yes, ma'am.
Okay, so we saw that so the question is to find the multiplicity that is going to be 1 for each. So this is solved and this is solved. Now, what is the defect of each eigenvalue? Let's find the defect of each eigenvalue. So what is defect? Defect means algebraic multiplicity minus geometric multiplicity, right? So for eigenvalue -1, so algebraic multiplicity will be what is the algebraic multiplicity for that?
1,
Yeah,
1.
and then the geometric multiplicity.
1,
Yeah, so it's going to be defect is going to be 0, right? So what is the defect of all the eigenvalues?
0.
So for all the eigenvalues, it's going to be 0, right? So um, so this is diagonalizable or not? So you're not going to
this
diagonalize.
is
Yeah,
this is diagonalizable because all eigenvalues are different.
that's true. Yeah, all eigenvalues are different as well as. So is it like okay? So okay, that will be my next question. If all the eigenvalues are different, like will the matrix be diagonalizable uh, if and only if all the vectors or all the eigenvalues are going to be different?
For diagonalizable, it is not necessary true.
Yeah, so okay, so next, okay, so let's frame a question. So let's frame a question now. So if a matrix, okay, so true of our question, a matrix is diagonalizable if and only if it has distinct eigenvalues. it's a true or false? As we already said, it's going to be false, right? Okay, we'll see some examples based on this. Okay, so remember this thing, we'll get into this later. Okay, so defect here is 0 for all eigenvalues. So this is going to be diagonalizable, okay? If it is, okay, and eigenvalues are all different, so definitely it's going to be diagonalizable. Defect also is going to be 0 for everything, so it's diagonalizable, okay? And the next, let's see the next question. Okay, so true or false question. An eigenvector for a given eigenvalue of a matrix is unique. True or false?
False.
Yeah. Yeah, arbitrary constant, right? It can be multiples of anything. Like we have t here, so it can be anything. So it's not going to be unique. Okay. So if next question, if A is a matrix, A is 3 by 3 matrix with eigenvalues lambda is equal to 0, 2 and -3, then A must be diagonalizable. I think this is easy for you.
Yes, true.
That's true. For example, if I'm saying it is 0, 2, 2, then what will you say for that?
Not necessarily diagonalized.
Yeah, it's
We
not.
cannot say.
You cannot comment on this basically. You have to see.
Yeah, we cannot say.
Okay, so next question is: A is a square matrix. Then for A square plus A is equal to 0. For this thing, lambda 1 is definitely an eigenvalue. True or false? For this matrix, I'm saying lambda 1 is definitely an eigenvalue.
Is lambda equals to 1 or lambda equals to -1?
Sorry?
Lambda equals to 1 or lambda equals to -1?
1, 1, 1.
Lambda equals to 1. I think the answer is false.
Okay. Okay, so let's see this. So A minus lambda I. So we can write it in this form, right? Eigenvalues, lambda is eigenvalue means. So I can write it as Ax is equal to lambda I x, right? So which means Ax is equal to lambda scalar into x. how can I write a square? A square, okay, so okay, so how can I write a square? I can write it this way. Which means lambda is a scalar, so I can get it out. And this we saw is lambda x again from here. So lambda into lambda x, so which means lambda square x. Is this clear till here? So this term a square x can be written like this, right? So a square x is equals to lambda square x, and ax is equal to lambda x from here. So a square plus a to x can be written as lambda square plus lambda into x, which means this has to be 0, because this 0 we got it, we have, this is going to be 0, right? No, okay, so lambda square plus lambda has to be 0, which means lambda plus 1, so 0. So lambda will be 0 and minus 1. Okay, so this is not true. It's a false statement. Okay, so I hope this is clear. So we gave this equation as a square plus a is equal to 0. So and we got it as this can be written as this form, and this is anyways going to be 0 as given here. So lambda square plus lambda is going to be 0 here. So we'll get 0 and minus 1. So one important thing to note here is matrix multiplication can be written. If you're getting a matrix, you're getting an equation for some matrix multiplication, you can write in terms of eigenvalues also. So this example says that whatever polynomial you are getting here, the same thing is it's same thing for the eigenvalues also. So that's one important point to note here.
Cayley-Hamilton theorem it is, I suppose.
Yeah. So this is important here. Okay. Okay. So next question. Eigenvalues of A and A transpose are same. True or false?
Is it just A transpose or A conjugate transpose, ma'am?
Yeah. Sorry.
The notation A power T denotes A transpose or A conjugate transpose.
What did you ask? A transpose or? It's A transpose. A power T is. This one is transpose.
Okay, ma'am. Then it's true, ma'am. The statement.
Yeah,
Yes, answer is true.
Yeah, it's true. It's a bit direct. Okay. So now if another question, if A is a singular matrix. A is a singular matrix if and only if it has eigenvalue, it has at least one value as 0. True or false?
True.
Why so?
If it is a singular matrix and if we are going to find out its eigenvalue, then 1 will be 0. And if one of the eigenvalue is 0, then determinant is product of the eigenvalues. Then product of the eigenvalue 0 means determinant 0. Determinant 0 means singular matrix.
Okay. So yeah, so when you find the eigenvalues, determinant of this thing has to be 0. So for that you will find the eigenvalues. And suppose if you have it's A is n by n matrix, then you are having n eigenvalues. Then you can write this whatever equations you are getting. If lambda 1, lambda 2, lambda n, they are the eigenvalues, then you can write it like this. Right? So when you are putting, for example, lambda is equal to 0, then you will get as lambda 1, lambda 2, lambda 3, lambda n as 0, right? So so if at least 1 is 0, it means that determinant is going to be 0, which means that it's singular matrix. So it's going to be true statement. So what I want to say here is for finding the determinant, you will make for finding the eigenvalues, you will make this as determinant of a minus lambda I as 0, right? And if, for example, you are having lambda 1, lambda 2, and lambda n eigenvalues for n by n matrix, n by n matrix, order of a is n by n, then you can write the same equation in the factorized form, like the lambda 1 minus lambda, all those things. Okay, so now if you are taking, for example, lambda is 0, which means that if you're putting lambda here as 0, then which means that determinant of a is going to be 0, right? Yeah, so you will be ending up with this equations. So lambda 1, lambda 2, lambda 3 is going to be determinant of a. Okay, so I'm saying it is singular, so determinant will be 0. Okay, which means that in this at least one eigenvalue has to be 0. So this is going to be true statement. So there is one more important thing here is determinant of a. You can express it in terms of product of eigenvalues. Okay. So next question is, if lambda is eigenvalue of, then what is eigenvalue of a inverse?
1 by lambda.
Yeah, so how can you get it? A minus lambda I x is equal to 0, and if I'm saying inverse, so I can
From
say
the
it as
definition.
a of x is equal to lambda I x, and if I'm saying inverse, I'm multiplying on both sides, then a inverse lambda I x will be there, so which means that x is equal to a inverse I x, and lambda I can get it here, so which means I can write this as a inverse minus lambda I x is equal to 0, right? So, sorry, 1 by lambda, yeah, so this is going to 0. So this is going to be eigenvalue, so this is going to be 1 by lambda is going to be eigenvalues for. So what if, so can lambda be 0 in this case? So do you have any doubt saying what if the lambda is 0?
Lambda cannot be 0 in this case. If it is 0, then inverse is cannot exist, no?
Yeah, so lambda cannot be 0 in this case because I said that minus 1 is there, okay? So minus, A inverse is there, okay? So inverse is possible only if determinant is not 0. Determinant is not 0 means, as I saw in the previous question, the lambda is also, there is no 0 in the lambda. None of the eigenvalues will be 0. Okay, so getting back to the our question which we discussed before, a matrix is diagonalizable if and only if it has distinct eigenvalues. So actually this is a false statement. So let's see some examples for this. So even if the eigenvalues are repeated, we can diagonalize the matrix. So for example, if I am taking the example, okay, for example, if we take a matrix like this, you know what will be the eigenvalues for this?
4, 4, 4.
So all will be 4, 4 and 4, right? So what is the algebraic multiplicity here? It's going to be 3.
3.
Right? It's going to, yeah, so it's going to be 3. Okay, so now, but if you find the eigenvectors here, so you know, if you find eigenvectors, then you'll be getting as okay, fine. So here you'll be getting as
Identity 0 equal to 0.
yeah. So from this equation, what you're getting? Yeah. So it's going to be see. So you don't have any equation. So everything has to be arbitrary here. So basically, you'll be getting eigenvectors as 0, 0. So you'll be getting the eigenvectors as is it clear till here? How we are getting eigenvectors for this?
Yes, ma'am.
So for eigenvalue 4, the algebraic multiplicity is 3, and also the geometric multiplicity, that's also 3, right? So defect will be 0. So if the defect is 0, then you can diagonalize the matrix. Are these vectors independent? So these 3 vectors are independent, right?
Yes.
Yeah. Okay.
Actually,
so,
they form a basis, standard basis.
yeah. So okay, let's take one more example. So if A is 3, 1, 0, 3, let me know if it is diagonalizable or not. So lambda is going to be 3 here, right? So algebraic multiplicity is going to be 2. But let's find what is geometric multiplicity. sorry. Substitute 3 there. So did you get this eigenvector like this?
Yes.
So what is the geometric multiplicity of eigenvector 3?
One.
Yeah, so it's 1 here. Okay, so defect, what is defect for eigenvalue 3? It's 2 minus 1, that is 1, right? Okay, so first of all, let me tell what is the geometric multiplicity and algebraic multiplicity. Okay, so first of all, okay. So if for a matrix A you have eigenvalues as lambda, and you will see how many times that is repeating. Okay, so that is for how many times the root of a characteristic polynomial is repeating. That will be your algebraic multiplicity. Okay, and for the eigenvalues, we will find the eigenvectors, and whatever is the dimension of the null space. You know, if you are getting so if you are solving a minus lambda I determinant is equal to 0 for finding eigenvalues, and you are getting eigenvalues which are repeated. Okay, so for example, it's like 1 1 something like that. So eigenvalue 1 is repeating twice, is coming twice. So how many times it's repeating, that is called multiplicity of if eigenvalue is 1, then algebraic multiplicity will be the number of times it's repeating. Okay, and then if you're finding but if you're finding a minus lambda I x is equal to 0, if you're trying to find null space, what is the null space? So if you're null space means the solution for homogeneous system, right, as we have seen in the previous classes. So for this, if you are finding the null space, what is the dimension of the null space? That is going to be keeping this lambda eigenvalue for a particular eigenvalue. You will try to find the null space of the eigenvectors and null space of this matrix, and for that the dimension of the null space is going to be the geometric multiplicity. Okay, so here we are having lambda as 3, so that is algebraic multiplicity. So we are having lambda is equal to 3 and 3. So for 3 algebraic multiplicity is going to be 2. Okay, because 2 times we are getting it. Okay, now for the 3, for eigenvalue 3, if I am trying to find the null space of a minus lambda I, that is we are getting here, that we are getting 0 here, 0 here, so 1 here. So we are getting as one arbitrary constant. So we have only dimension as 1, we have only 1 here, right, one basis here, one arbitrary constant t here. Okay, so the geometric multiplicity here is going to be 1. Okay, so for lambda is equal to 3 eigenvalues, the defect is going to be 2 minus 1, that is 1. Okay, so if the defect so the one main important thing for the matrix to be diagonalizable is for each eigenvalue the defect should be 0. Okay, so for example, if we saw here that lambda is so the eigenvalues are 4 4 4. So for eigenvalue lambda, for eigenvalue 4, the multiplicity is 3 because coming twice. Okay, but if you are seeing the eigen vectors for lambda is equal to 4, here matrix is such that we are getting three null space dimension is 3, right? We are getting 3 vectors here, so 3 bases, so dimension is 3 here. Okay, so 3 minus 3 is going to be 0. Okay, so though we are getting the eigenvalues same, all the 3 eigenvalues are same, but still the geometric multiplicity is going to be 3, same. So we are getting independent vectors, 3 independent vectors. So the defect is 0 here. so it's diagonalizable. Okay, so you cannot comment that based on distinct eigenvalues you are going to get I mean even just by seeing, like for example, even if the eigenvalues are not distinct, still there is a possibility of getting the still we can get the we can diagonalize the matrix. So with that we can say a statement that for a matrix A to be diagonalizable, either two things you can check. One is defect for each eigenvalue has to be 0. If it is more than 0, then you cannot diagonalize it. And also the number of independent eigenvectors should be of size of if A is n by n matrix, then you must have n independent eigenvectors so that you can diagonalize it. So as you see here, these are independent vectors. Is it clear so far? Can I move on to next question?
Yes, ma'am.
So as we saw here, so a square matrix is diagonalizable. We are not solving questions on numerical questions on diagonalizing a matrix because it's going to be very lengthier. It has n independent eigenvectors. It's a full set of eigenvectors. Okay, so it's a full set of eigenvectors. Or you can say that for each eigenvalue, or you can say for each eigenvalue algebraic multiplicity is same as geometric multiplicity. Or also you can say that defect for each eigenvalue, defect has to be 0. You have to check these things to see if the matrix is diagonalizable or not. Okay, so next question we'll see. So you have these two matrices. So tell me if these two matrices are similar or not. So are these two matrices similar or not?
Not similar.
Okay, so how do you say that? So for two matrices to be similar,
one of the determinant of A is one of the matrices has determinant 0, another one has determinant non-zero.
sorry.
from the given two matrices, one of the matrix has determinant 0, another matrix is determinant non-zero. So one of them is singular, another one is non-singular. So they can be similar.
So in case if both the matrices you are having their determinant is not zero, then how will you say that? In case so I think maybe in this case you are having one as zero, another is not zero, but in other case when you get two matrices when
Then there we have to check. Here I have seen that because similar matrices they should have the same eigenvalues.
yeah, that's true. But in
So that
what is the method for generic case like?
definition you were asking.
Yeah,
Definition of two matrices being similar.
yeah.
Yeah, then there should be some non-singular matrix P such that P inverse AP equals to B in A and B are similar.
So there should be a matrix of, so for A and P to be similar, there should be a matrix P such that P inverse A P is going to be we'll give you this. Okay, so that's okay. So using this can we really solve? Okay, so see, so one more thing to say is if two matrices are similar, if and only if their eigenvalues are same. With not just this, okay, not just this, it's also like with same multiplicity also, okay. Okay, so for example, if you are getting a characteristic equation such that lambda 2 square lambda this thing, for example, if you are getting it like this characteristic equation, whatever you are getting like this, for example, then you know that 2, 2 and 3 will be eigenvalues for this case, and suppose if it is like this, then here you're going to get as 2, 3 and 3, right? So here 2 and 3 are eigenvalues and here also 2 and 3 are eigenvalues, so but multiplicity is not same. So for this here 2 multiplicity is 2, again 3 is 1, and here for multiplicity 2 is 1, and for 3 it is 2, right? So what I want to say is the two matrices are similar if and only if their eigenvalues are same with same multiplicity, okay. So you can check the eigenvalues for this thing to know this method is going to be lengthy to find whether there is P existing or not. That's going to be lengthy, but this will be handy for you. So let's try to find eigenvalues for this. So okay. Okay, so when is lambda? ultimately we are going to get as so this is the characteristic equation for matrix 1. So let's see the characteristic equation for the matrix 2. So we can get it as this will be so ultimately the equation which we are going to get is so this is characteristic equation for matrix 2. So seeing these two equations, can you comment whether the eigenvalues be same or not?
If the characteristic equation are same, then also we can say that metrics are similar.
Sorry, I didn't get you.
If we have two matrices with same characteristic equation, then both the matrices are similar. That we can conclude.
Yeah, so seeing these two things, you see all the eigenvalues and for each eigenvalue even the multiplicity, they both have to be same for two similar matrices. Okay, so in that case, for example, if we see here that for a polynomial for so if two polynomials has same roots, with same multiplicities, they must be either same or they must be in some relation of some multiples. So for example, if the root is 2 and 3, so you can get equation as so some equations like lambda square minus 2 lambda minus 3 lambda plus 6, which is equals to lambda square minus 5 lambda plus 6 equals 0. So you can have in the multiples of 2 like this, some multiples of this polynomial like this, like 2 lambda square minus 10 lambda plus 12 is equal to 0, or some multiples, basically multiples. So even if multiples are changing, for example, this has multiple as 2 and this has multiple as 1, and another polynomial you are taking as multiple as for 2 as 1, and for 3 you are taking as multiple as 2, so then it is going to be like, okay, and for this it's going to be like, lambda minus 2 and lambda minus 3 the whole square is equal to 0. Okay, so both are not going to same. Okay, so if so both polynomials, if you expand this, they are not going to be same. Okay, so if you have to have for having same roots, same eigenvalues with same multiplicity, the characteristic equation both have to be same, or at least they have to be multiples. Okay, so these two matrices are not similar. Okay, so you can you need not directly solve the eigenvalues, you can get till the the characteristic equation and observe that, and you can comment on how the eigenvalues, at least you can say whether the eigenvalues will be same with same multiples or not. Okay, so that's one thing. So this is not going to be similar. Those two matrices are not similar matrices. Okay. So next question. So are these matrices similar?
Yes.
So how we are saying 3 minus lambda 1.
Eigenvalues are 3, 2 because it is a diagonal matrix. So, sorry, upper triangular matrix. So, no need to find out eigenvalues. Diagonal elements are the eigenvalues.
Yeah. So if you solve the theorem, so you are getting eigenvalues same and same multiplicity. So and here also it's going to be okay. So you have same eigenvalues with same multiplicity. So you can say that both are similar. I think we'll be closing this session soon. So, are there any doubts so far?
No doubts, no.
Or any doubts in assignment or something you can ask? If not now, at least in the next class we can discuss about it.
Ma'am, are you going to discuss about isometry?
Isometry I have discussed. I think you joined late, so
Okay,
even
so
before that,
in
even
the
the
if
question.
you have time in the end of the interaction, you can just give me a gist of that in just 1 or 2 minutes.
Yeah. So one more thing was discussed is there was a doubt in the last question. There was some mistake was done in the last question in a question in the previous session. So that was also discussed there. So you can go through even that.
Okay, ma'am.
So if you see the video from the this videos will be uploaded, so you can see that also to know whatever is missing. So isometry basically we have seen various questions on that. Like for example, we have gone through what is the definition of for linear transformation to be isometry. We said that it is it should preserve both the length of the vectors as well as the angles between the vectors do not change. So if that is the case, then we can say the linear transformation as isometry. And we have discussed that for isometry, they have to be the matrix. If the isometry, the transformation is represented as a matrix, then those matrices will be orthogonal. So we have seen few examples on that. And we have also seen examples of if matrix is orthogonal, then its inverse is going to be the transpose of the matrix. Certain things we have seen. So you can go to the video and you will get to know.
Okay, ma'am. Thank you.
Yeah, any other doubts?
No doubts, ma'am.
So so then we can meet in the next section. So is everything clear? Like are all the concepts discussed? Like do you feel anything is left out? Yeah, then shall we close the session and meet in the next session? Yeah, thank you so much. If you have
Yeah,
any
sure, ma'am.
Yeah, if you have any doubts, then stay back. Else, we'll meet in the next session. Thank you so much.
Thank you so much, ma'am. Thank you.